Class, welcome back to Electromagnetics. Again, we want to continue part 8, second lecture here in that part of the course where we're talking about waveguides. So we want to look at transverse electric waves. We'll first look at a historical background for this gentleman. Educated at the University of, I guess you pronounce that, Leiden. He worked there as well. This is his picture. This is a more modern contributor to electromagnetics. His name is Hendrik Lorentz. So we've already looked at the Lorentz equation where it related the force on an electron due to an electric field and a magnetic field if it's moving. Some of the notable things for Mr. Lorentz: he won the Nobel Prize for Physics in 1902. He was a colleague of Einstein and laid the foundations for him to produce the theory of relativity. Another equation that he came up with, if you take modern physics, that took into relativistic effects when you approach the speed of light. One of the major components of this, again, was the Lorentz transform. That's what I was talking about. And then he derived the Lorentz force relationship, again, that we've seen earlier in the course, where we see the effects of the electric field and magnetic field to either a stationary charge or a moving charge, how it exerts force on that charge. So again, part 2, second lecture of part 8, transverse electric waves and parallel plate waveguide. So again, up to this point, we've been looking at electromagnetic propagation in terms of straight paths down the z-axis, but now we want to extend this to see how waves can travel at oblique angles and how they can be guided in desired directions with the use of a waveguide. And so we looked at the mathematical adjustments last lecture, so let's see how we can utilize those. So to do this, we want to consider the superposition then of two uniform plane waves that are propagating symmetrically with respect to a z-axis as shown below. So again, let me get my laser pointer activated here. So here's z-axis, so this will be the direction of propagation. And so we're going to have two different waves, electromagnetic waves here, both making an angle of theta with this x-axis. And so you have this E1 that's going in and out of the board, and this E2 which is also going in and out of the paper or board. But then we have this magnetic field, which you can see it's going to vary because we flip or we mirror across this junction right here. And so we can define our electric fields then with this new mathematics that we've introduced last time. So this E1 is going to be this peak value times this cosine omega t times this phase constant vector B1 dotted with R, which is going to give us this direction AY. Of course, that's due to going in and out of the board in the Y direction. This E2 is very similar, except we're going to go negative here, so it reflects or mirrors on this side. And so we'll have this new phase constant giving us this new direction for the second wave. So that being the case, we can define or expand our first electric field by putting in the definition of this beta. So it'll be bx cosine theta minus beta times z sine theta. We saw how we can expand this the last time. And again, the E2 value, same thing. We flip the sign here because we mirror it, but then we have a negative bx cosine theta, but still a negative z sine theta. Okay, so this is just the expansion of these two, expanding this beta dot r term here. So with these, we can now define our magnetic field. So we have this H1 now, and so using what we saw last time and plugging those values in, we now have an expression for our magnetic field which is just the electric peak over the intrinsic impedance times this new directional vector, which takes into account that it's oblique compared to the z-axis, and then this argument here. And then, of course, our second magnetic field on this side, again, we're just going to have this negative sign here because we're mirrored across the x-axis. And so now we have expressions for our E1H1 and our E2H2. So now we can use superposition as a tool here that will let us be able to derive a general expression for the E field by combining these two equations above. So when we do that, we'll just come up with this new E vector, our electric field vector, which is just the addition of the E1 and E2 vectors here. Of course, when we do that, we just simply plug in the values from above and do some mathematical rearrangements, and when we do our new expression for the resultant electric field is this equation here. So likewise, we can do the same thing with the magnetic fields. We can use superposition to come up with a composite magnetic field, which will just be the addition of H1 and H2. Plug those values in, and this is the result there. So now we have expressions for our composite electric and magnetic field. So we need to pause here for just a minute. Of course, we see that our E field is just going in and out of the board, so that's this AY, and then our H field, we're going to have a Y and a Z component, which gives us the oblique angle that we talked about on each side. So if we examine these two equations, we make two very important observations. The first is that in the Z direction, we have traveling wave characteristics. Okay, so that's this guy here. We notice in the X direction, we're going to have standing wave characteristics. That is, the wave doesn't seem to be alternating. So if we're going the Z direction, of course, it's propagating down, but in the X direction, it's just going to be a standing wave. So what does that look like? Well, it looks like this. So if we take the E field here, we go down the Z-axis. So this is the Z-axis, and this is the X-axis. In the Z-axis, you see we go from Z, take this point right along here. We start at 0. It starts to go up in that direction. It increases in that direction, decreases, goes to 0, pops up on the other side of the axis. And so it's kind of a sine wave propagation that we see there. But in this X direction, it's just this standing wave. We just pick this point in time, and this wave is just standing there. It's not moving. It's not propagating. These nodes are always 0. But that's not always the case going in the Z direction. So with expressions for the electric and magnetic fields, we can now compute the Poynting vector from the composite wave, which is, gives us some information about the power. And so we remember from previous lectures that the Poynting vector is just the electric field crossed with the magnetic field. And so in this case, we've got just a Y component on the electric field, but we have X and Z components for the magnetic field. And so when we expand this out, this is what we have. And when we plug in the values for that, this is the resultant vector for the Poynting vector. Well, what would be more interesting to us then would be the time average of this Poynting vector, so we can know, the average power that we'll be using. And so when we do that, we plug these two, we come up with these two components here. When we take the time average, and the only part that's going to be affected by this will be these two sine functions here, because they're the only ones that have any reliance on time itself. These others are constant when it comes to time, so that's why we put the little brackets here around just the sine, because they're the only ones affected by time. So when we look at these, if we can remember back to trigonometry and maybe some calculus, maybe we will recall that when we take the time average of a sine squared function, that's always going to equal to a half. If we take the time average of just the sine function, that's going to always be 0. So because this one's 0, this whole second term just drops out, and we're left with just this first term divided by 2, which that gives us this resultant expression here. So this is our time average power. You can see it's all along the z-axis because that's where our direction of propagation is. So again, this tells us then that all of the power flow is in the z direction, which means that our resultant wave is a transverse electric, or you'll see this a lot of times as the TE, transverse electric wave, since our E field is transverse to the direction of propagation. So remember, we're transmitting in the Z direction, which is going like from left to right, but our E field is going in and out of the page, so it's transverse. Now you can have the flip situation where the magnetic field is transverse in and out of the paper, and when that happens, then we would call this a TM wave, or a transverse magnetic field. So you'll see TM waves and TE waves, and that just means which field is transverse to the direction of propagation. So this brings up some pretty interesting scenarios and things to look at. So an important thing to note here, looking back at this graph, is that the electric field is 0 for all t and z when the sine of beta x cosine theta is equal to 0. Well, this occurs when beta x cosine theta is some whole number multiple of pi, where we can just let m in this case equal to 0, 1, 2, on forever, just integers. Well, this also occurs for values of x, up and down, that's our x direction, of m pi over beta x cosine theta, which is, just doing some substitution, m multiples of the wavelength over 2 cosine theta. So that means that these nodes here are always 0. There's never anything happening there with the electric field at those points. And again, this is where our wavelength is defined as 2 pi over the phase constant, or 1 over the frequency times the square root of permeability and the permittivity. So this is pretty interesting then. The above two relationships are pretty extraordinary for the scenario, in that the first equation then tells us that if we were to place perfectly conducting planes in these intervals where we saw those nodes for x, that is for a given wavelength, that a wave between these planes would propagate undisturbed as if the sheets were not there. So it wouldn't matter if the sheets were there or not. Since the E field is always 0 there, it would never know. And we can prove this pretty easily with Maxwell's equations and what we've done up to this point, seeing that the boundary conditions there would be satisfied at these intervals of x for the x component of the field. This means then that the conducting sheets placed at intervals of x then would guide the wave, or more importantly, guide the energy or the power in the direction of propagation parallel to the plates in the z direction. This is why we call this a parallel plate waveguide. This is a little different from the parallel plate transmission line that we looked at in the previous section. In that scenario, the uniform plane wave slides parallel to the plates, so it's kind of propagating along. In the parallel waveguide, the oblique wave bounces back and forth between the conductive sheets, and so that's an important difference between those two. So when we examine this relationship for the spacing of x above, we note that at this distance, this provides the minimum spacing to the first half-wave node, or lambda over 2 in the x direction as seen below. So we'll get this lambda over 2 distance here between here and here. So the propagating wave, you'll just see a half wave, which is just that first hump that you saw in the previous graph, where the one node's here and one node's there. So then for every step in M, we add another half node. So if we were to take this down to 2 lambda over 2 cosine theta, so I'd move this plate down twice as far, then we would see a full sine wave in between there. There'd still be the node in the middle, but the plate would be at the second node. So since there are multiple conditions for which a wave will propagate, each one of these M's where we put the plate, adding another half wave, we have a way to distinguish which multiple of x we are using by referring to this as a mode, where the mode is determined by the value M in the above equation. For the case in our example, where the electric field is transverse in the x direction, we would refer to this then as the TEM, 0 mode. So that M will be an actual number. Depending on how far apart our plates are, the further and further we separate them, we're allowing more and more half waves to propagate, so it'll be a higher and higher mode there. And again, where the first subscript in this is the mode in the x direction, and the second subscript is the mode in the y direction. So you can have parallel plates on both sides, and that's what we might talk about a little later as a rectangular waveguide, which is just an extension of parallel waveguide. But remember that this mode number refers to the number of apparent half wavelengths there are in the respective direction. So if we now consider a general parallel plate waveguide with conducting plates located at x equals 0 and x equal a, then for the TEM0 waves guided by the plane, we have that this distance a should equal to m lambda over 2 cosine theta. Or we could say that cosine theta, remember the theta is the propagating, the angle that we are propagating into these plates, is equal to this expression. So this suggests that as the frequency increases, the angle required to propagate is very small. And so then as frequency decreases, the angle increases, and we can see this on the next slide. So what we see here then, this would be DC, so there'd be no angle. So as we start to increase the frequency of our wave, this is the angle we'd have to shoot it in between the parallel waveguides to get it to propagate. And as we go up in frequency, we have to tilt that angle more and more until ultimately we get to a point to where it just bangs back and forth. So in the last case shown previously, the wave merely bounces back and forth, like I said, and the wave is technically not propagated down the waveguide. So this occurs at this cutoff, we call it the cutoff wavelength, which is 2a over m. And so here we refer to this with this lowercase c, indicating this is the cutoff wavelength. And so this can be rearranged then to a frequency. We can have a cutoff frequency, which is equal to this equation here. We'll examine that more in here in just a second. So since each of these cutoff equations above is a function of the mode, or m, this means that there is a separate cutoff wavelength or frequency for each mode in the waveguide. This would indicate that for a given waveguide, that as we increase the frequency of the transmitted wave, we would continue to induce more and more modes of propagation. So we can have multiple modes propagating at the same time. This also tells us that the propagation for a particular mode is only possible when the frequency is greater than this cutoff frequency. That is, that we get above the point to where it's bouncing. So now if we substitute this cutoff wavelength, or the definition of it, 2a over m, in our original equation, we have that the cosine of the angle is equal to either lambda over the cutoff wavelength or the cutoff frequency over the frequency. So we can do some mathematical manipulation here where we finally come up with beta cosine theta is equal to 2 pi over a, which is equal to this relationship here, which this is very similar to the Lorentz transformation that we spoke about when we were talking about Lorentz earlier. So this last equation is interesting because this tells us that the phase constant in the direction of propagation is only real when our wavelength is less than the cutoff wavelength. Otherwise, it's imaginary. This offers some explanation as to the phenomena of the cutoff frequency, why it cuts off, because our wavelength won't be real anymore once we get to a certain wavelength. We can also define now the guide wavelength, that is the wavelength in the apparent direction of propagation in the z direction. So remember, we've got two electromagnetic waves that we're superpositioning on each other. They each have their own wavelength, but the wavelength that you see that it's appearing to go down the parallel plates is defined as follows. So it's lambda over 1 minus lambda over lambda c squared. Again, this is very similar to the Lorentz transformation, is what happens as you start to approach the speed of light. So likewise, we can define phase velocity in the z direction as well. So the apparent phase velocity in the z direction, where this is the phase velocity of our two waves that we're superpositioning together to get the resultant one. So finally, with this new understanding of modes and cutoff conditions and group velocity, we can now substitute the mathematical concept back into our original equations for the electric and magnetic fields for a parallel waveguide. This is our electric field, and this is our magnetic field. So these new expressions for the TE propagating mode fields in the guide do not contain the angle theta, which is pretty interesting. Now, that's a little misleading because A, the definition of A, if you go back and look a couple of slides, actually has theta in it, but A, for the most part, though, is really just the separation of the plates. So it's kind of there hidden, but not really. In reality, it's not. So let's look at a quick example of how we apply this then. If we consider a parallel plate waveguide with a spacing of A between the two plates of 5 centimeters, so we got two conducting plates and we separate them by 5 centimeters apart, what are the propagation or cutoff conditions for the TE modes for a waves, electromagnetic waves that have a frequency of 10,000 megahertz or 10 gigahertz? Well, we know that the general cutoff wavelength can be expressed as 2a over m. So in this case, that would be 10 centimeters or 0.1 meter over m. And the cutoff frequency, again, we're assuming free space is what's in the guide. You could technically have a dielectric in the waveguide, but that's very uncommon. It's going to be 3 times 10 to the 8 over our, which is the speed of light, over our cutoff wavelength. And so in this case, it's 3m times 10 to the 9 hertz. So what does this mean? Well, this is how we determine, which modes are going to propagate. So the propagating modes then can be determined as follows. So for the TE10 mode, that's the first mode of propagation. We put a 1 in for m, that gives us 3 times 10 to the 9 hertz. Well, we determined that we're propagating at 10 gigahertz, so that's 10 to the 10 hertz. So since this is less than the cutoff frequency, we're not to the point where we're bouncing up and down yet, this mode propagates. So we do have a TE10 mode propagating in this condition. What about the TE20 mode? Well, in this case, we put a 2 in here, And so that means our cutoff frequency is 6 times 10 to the 9 hertz. This is still less than 10 to the 10 hertz. So this mode will propagate as well. So we have both modes propagating so far. TE3 mode, we put a 3 in here. That's going to be 9 times 10 to the 9 hertz. That's still less than 10 to the 10. So this mode propagates as well. So you've got 3 separate modes propagating. So that's 3 different wavelengths, half wavelengths. So you'll have, this will be 1 half wavelength between the plates. This will be 2 half wavelengths between the plates, and this will be 3 half wavelengths between the plates. So all 3 are propagating. What about the 4? Well, if we do that, put a 4 in here, that's 1.2 times 10 to the 10 hertz. That's greater than the cutoff, so this mode will not propagate under these conditions. So for these modes, we can now calculate their wavelength, at least down the guide, and our phase velocity. So if we were to plug in these values for each of these, we would see that our cutoff wavelength are these values here. That just comes from plugging in those values there. Cutoff frequencies, which we've already calculated, the angle that they would be propagating at, and then our apparent wavelength from the superposition of both our electromagnetic waves would be this. So you can see as we go up in modes, our wavelength increases, and there's a pretty big jump from the second mode to the third mode. Likewise, our phase velocity, you can see that it goes up as well as we go up in modes. So interesting example here of how waves propagate down a waveguide.